performance engineering, or the performance trifecta, and how that relates to many optimizations at the JVM level. The Java virtual machine that I am most familiar with is called the HotSpot virtual machine, and you have the Oracle HotSpot virtual machine as well as the OpenJDK, which are pretty similar. So about me, more about me. In the past, I've worked with companies like Advanced Micro Devices and Sun Microsystems and Oracle. And what that has helped me is become a holistic performance engineer. Because with Advanced Micro Devices, I was a compiler and a JVM performance engineer and was concentrating on x86 64 architecture. And then with Sun, it was also Spark. And then Oracle, I was more from the JVM performance viewpoint, and I was doing more of garbage collection. And my last job title at Oracle was G1 GC performance lead, which is the latest garbage collector in OpenJDK. I am now independent, and I manage runtimes issues, basically anything running, any application running on top of the Java virtual machine. Okay. So like I said, this is very interesting to me because I'm going to lay out the performance trifecta, and that's how we're going to start. We're going to start with the characters. So I'll talk about the HotSpot virtual machine, its execution engine, and then the performance trifecta. And then we'll try to build a storyline, like how these things, the throughput and responsiveness, how it drives these performance innovations. Okay. So let's get started. So if I had to draw block diagrams, black boxes for the HotSpot virtual machine, you would see something like this. There's of course a virtual machine, and your Java application is running on top of the virtual machine. Of course, there are many things in between there. Your application could be in the cloud, the virtual machine could be in the cloud, lots of things. But at the basic level, this is what it is. And then there's a hardware somewhere, right? It has to run somewhere. So, and then you have some Java API. What users know as the JRE, which is the Java Runtime Environment, which is what you download from Oracle's website or OpenJDK, is nothing but the Java virtual machine and the Java API for HotSpot. Today, we're going to concentrate on the Java virtual machine and its helpers, which means the execution engine. So when we talk about the execution engine, there are two things. Okay, one is the runtime, and then the execution engine itself. Okay, so let's look at the execution engine first. So within the execution engine, you could divide the things again in two different ways. You could talk about heap management, which is your automatic memory management, which is a good thing that Java brings about. And then you have something called compilation, which many of us know as just-in-time compilation. But there are different flavors of just-in-time, and I'm going to talk about that as well. So if I ask you what is garbage collection, I know many of you would jump and answer saying it's reclamation, of course. You're reclaiming heap space, right? So if the objects are dead, you want to get your heap space back. But it's not just that. It's also the allocation. Yeah. So if I just say garbage collection, and reclamation is, of course, one of the work it does, but there is also the allocation that happens by the allocation threads. And then there's promotions and all those things. So we'll talk more about that. But always think of garbage collection as this cohesive effort between allocation and reclamation. It's not just reclamation by itself. You're responsible for the allocation also. And sometimes you could pay a price based on the allocation rate and stuff like that. What about compilation? So when we talk about compilers, and that's actually where I started my performance career, was static compilers, C++ compilers. And then along the lines of static compilers, there's something called ahead-of-time compilation. Okay? In Java 9, you'll find a basic, very, very rudimentary flavor of ahead-of-time compilation, but that's just the start of it. So when we talk about ahead-of-time compilation, it's usually done to improve your startup, the application startup. And what happens is that it kind of helps just-in-time compilation because so if you have any shared classes or libraries, you don't every time you encounter them, you don't have to just-in-time compile them, right? You could have an optimized version of it, and you can store it. So it's compiled ahead of time, so that's the optimized version, and then you can reuse it. So it helps, like I said, with startup, because you don't have to wait for the profile-guided optimization to tell you that, hey, yes, it's important, it's hot, let's compile it. Because you already have optimized version, just load it. So the other two flavors of compilation is what HotSpot is known for. And it's called profile-guided, which I'll talk more about what it means, and then something known as adaptive optimization. So adaptive optimization would be, you may be used to, intrinsics, like in static compilers, we have intrinsics. But the intrinsics in HotSpot are slightly different, more smarter. There are other things like inlining. Adaptive optimization, the biggest bang for the buck is in inlining. And HotSpot engineers have optimized inlining to the core. So, and then there's something known as dynamic deoptimization, where, for example, you have compiled a method, but very soon you have, say, for example, in tiered compilation, you realize that, oh, my level of compilation at T2, which is the client, was not as optimal as it would be if I compile this at T4 level. So then what you do is the T2 level of code gets de-optimized. So that's called dynamic de-optimization. So that's also something that HotSpot gives you. So we'll talk more about that shortly. Let's look at runtime very quickly. So we all know the runtime as your interpreter, right? Runtime means interpreter. But there are other tasks that runtime does, and I'm not going to spend more time on those tasks. But there's the VM class loading, you have bytecode verification, exception handling, synchronization, of course, thread management. And to read more about it, you can go to that link, and it's a very good runtime overview provided at the OpenJDK java.net link right there. So if somebody asks you, what's the runtime goal? So you are given, so by you I mean the JVM, is given the bytecode. So what's its goal? It's not just to make it faster or anything. It's just to convert that into native code. That's the goal. The goal is I get bytecode, I convert that to native code. And that's what it is. So it's not really, it doesn't have performance in mind, right? So with that knowledge, what drives innovations in performance, right? What makes you want to make things more performant? Well, there's the trifecta. And many times, many performance engineers will talk about this. So this trifecta is called, to me, it's responsiveness, which people also talk in terms of latency, right? And then it's footprint, which is basically your size, and then throughput. So if I had to define responsiveness, I'll say the time until I get a response back. Simple as that, right? My stimulus could be something that, like transactions, or like your start of a transaction, or read requests, or database access. So these are my stimuli, and how soon do I get the response back? Simple. What about footprint? To me, footprint optimization is twofold. Can I fit in more? So I have this space, and I want to fit in more, right? And then the second is, can I remove redundant objects, right? Redundant data, so that I can compact. So I have this space, and I want to optimize it by getting rid of things that I don't need and kind of compacting it, okay? The reason I'm defining it right now is because when we talk about these optimizations in the JVM, you'll realize the motivation behind them, okay? And then throughput. Throughput is simple. How much can I push through? I have this box, and I want to optimize it, so I want to push as many operations per second as I can, right? So now let's look at the first trifecta, responsiveness, and how that affects how the optimizations that are done for responsiveness affect the execution engine. So let's start with the garbage collection. So to optimize for responsiveness, we have faster allocation paths, and I'll go into details about each of them, but these are known as thread local allocation buffers. So when your application threads are trying to access this one heap, one Java heap, single Java heap, what happens is you don't want it to have lock contentions and stuff like that. So you give each of them their own local allocation buffers, right? And the only time they have to contend is when you're trying to get a new buffer, right? Within the allocation buffer, it's just bump the pointer because each thread has one. So it's more responsive. What about faster reclamation? So some of the garbage collectors, actually there's only one, that doesn't do compaction at all. It just does in-space deallocation. So what that means is that if it finds that an object is garbage, it just deallocates in space, and it maintains a list of these free spaces. So there's no compaction, you're saving time, your application is more responsive. What about doing work concurrently? So what's the job of garbage collection, reclamation? It's you mark, you sweep, and then you could compact or not, or you can partially compact. So what if you could do most of the work concurrently? So what if you could do marking concurrently or partially concurrent or sweeping concurrently, right? So that way, again, you're trying to avoid the application not responding. You're trying to avoid spending more time in garbage collection, okay? What about responsiveness and compilation? Of course, I spoke about ahead of time compilation. Remember, your application does not have to stay in interpreter. You can go and have these shared classes and libraries loaded in the compiled, in the optimized state ahead of time. So now your startup is faster, your application is more responsive at startup. Adaptive optimizer, again, I spoke about the optimizations, there's vectorization and all those things, where you can get as if you're running on directly on the hardware, so you can have hand-optimized code that is running directly on the hardware, so you get your static compiler-like performance, right? And then locking improvements. And locking improvements is very interesting because it's something that I talk about in runtime as well, because responsiveness and runtime, so locking belongs to both compilation as well as runtime. So what are the locking improvements? We know about bias locking, which is for uncontended locks. Then there's lock coarsening, then lock elision. There is, in JDK 9, in Java 9, you have something called optimizations for contended locks. So remember previously bias locking was for uncontended. There's only a single thread that has a lock, so you can optimize the lock away. But now if you have contention, if you're two threads trying to get to the lock, there's optimization in Java 9 that can help you with having faster paths and trying to do some aggressive assumptions saying that certain things may not happen. So it generates a fast path for locking algorithm. There's also class data sharing. Again, you have something that's common, so you could share it. And And that's people know it as CDS. It's available with certain garbage collectors. It helps reduce startup time because you are creating a shared archive of those classes. Okay? So now we have covered all three aspects of the JVM with respect to responsiveness. So now we can move on to footprint. Okay? Footprint in garbage collection. We have, of course, compaction. So remember, when I was defining footprint, it's not just how much can I fit in my space, but also can I remove redundant things or things that are no longer needed. And that's what is meant by compaction. So compaction in garbage collection, especially in HotSpot, it can happen in different ways. But the gist is that you're trying to move live objects together to trying to take, so if you have a long-running application and you have, say, in-space deallocation, what would the heap look like? It would look like something like like holes in it, Swiss cheese, right? So even though you have this free space, but your objects may not fit, so you're trying to match pegs and holes, right? And it becomes very tiresome, and eventually you'll have fragmentation and promotion failures and stuff like that. So compaction combats that. It combats fragmentation. So you move, in the old generation, you'll move the live data to the lower end of the heap. During the young generation, and I'll talk more about that, the compaction happens such that live objects are moved into survivor spaces. So that's compaction, and it helps with footprint. There are a lot of algorithm refinements in reducing allocations. So you have some things like how do you do copying, depth first or breadth first, or you have alignment. Object alignment is the biggest refinement. So that way, your processor, it's done so that your processor can access objects and doesn't have to do calculation every time it's trying to access an object. And then compressed headers. So Java objects have header and body, right? So every object has a header. So compressed headers basically compresses those headers. And that's an optimization in saving footprint. So it's per object optimization. So it's really efficient. What about footprint and compilation? You have inlining. So now, because of inlining, and HotSpot does pretty aggressive inlining, you can avoid invoke call overhead, right? And then there is something called escape analysis. So if I know that my object is not going to escape my method, I don't have to allocate it on the heap at all. I can allocate it out of my processor register. So these are the optimizations that help with footprint. There's also the deoptimization that I talked about. So I can help my code cache by taking away and zombieing, like reclaiming that code. So I'm optimizing for space again. So these optimizations within the virtual machine help not only the caches within the virtual machine, but also they are processor cache sensitive. So they understand, they respect the processor cache needs, and so they can do co-location and all those things. So these things are very footprint sensitive. What about runtime? I'll talk about compressed oops and class pointers in detail. Actually, I'll have an example how that happens, if we have time, of course. But the gist of it is, when you have a 64-bit address space and you have a 64-bit virtual machine, you don't have to use all the 64 bits to address the pointers. So what you could do, you can compress these ordinary object pointers. That's what OOPS stands for. And you can use now only 35 bits to address up to 32 gigs of space. In theory, 32 gigs. In reality, it's about 28 gigs. And we'll see an example of that. And similarly, you can do class pointer too, because that's a part of the header. So you can reduce class pointers accordingly. Code cache, as I mentioned that. So code caches are where your JIT compiled code stays. It helps footprint, right, of course, because you can reuse this compiled code, right? You have to just access the code cache. You don't have to store, every time you compile, you don't have to store, you can just look it up in the cache. And class data sharing, we already mentioned that. What about throughput? So with respect to GC, and this is throughput optimizations are probably the most, especially with respect to garbage collection. So to give you guys a background, OpenJDK HotSpot GCs, most of them, do stop-the-world collections. What that means is that your application threads come to a halt, and then your garbage collection threads start working. And imagine if you had a single garbage collection thread, and you have 200 gigs of heap, and then you have your process. You have about, say, 32 cores, but you only have a single garbage collection thread. Is that going to benefit you at all? No. And that's going to hurt your throughput and actually everything, responsiveness and everything, because you're stuck doing garbage collection. So one of the biggest optimization is multi-threaded garbage collection. And not just that, it does work stealing. So if I'm a thread, garbage collection thread, and I'm done with my work queue, guess what I can do? I can steal work from some other garbage collection thread, and we can all try to finish at the same time. So that is queuing algorithm and everything is used to optimize the multi-threaded work queues. Also multi-generational heap. Remember I said 200 gigs of heap. Imagine if you had a single generation. Your throughput is going to be really, really bad, because every time that single generation gets filled up, you have to, which will be very often, because in theory and in practice, most objects die young, right? So if you had this thing and filled up, which will fill up based on your allocation rate, fill up really fast, and then you have to collect the 200 gigs of heap. Instead of that, if you had an area where you can allocate these young objects, and then you kind of have a sieve, only promote objects that can pass through this fine mesh. That would mean that you're aging these objects, and then these long-lived objects would go and sit in the old generation. So you have two different collections. You have the young collections that will happen often, and then you have a collection for the old generation, which will not be as often as the young collections. So that really helps throughput. And that's what I mean by multi-generation. Multi-phased marking. So remember I said marking can be partially concurrent and partially stop the world. So that's what it means. So do some work in concurrent fashion, do some work in stop the world fashion. You need to stop the world in HotSpot, many of the HotSpot garbage collections for initial mark, and then for marking at the end after your concurrent phase is done. So if you could break it up into multi-phases, then you can do some work concurrently and some work in parallel in stop the world fashion. That will help throughput, and it does. And then you have compaction. Don't do a monolithic compaction. What if you did incremental compaction, which is what first garbage collection does? It does incremental compaction, so that helps throughput as well. Throughput and compilation, of course, JIT itself, right? The moment you start the adaptive JITting, it's going to help your throughput a lot, because it's going to be more responsive. Your application's going to be more responsive. Intrinsics, I will talk more about that, but this is basically a hand-optimized code that anytime you call these code patterns, you will go to this hand-optimized code and just use that. You don't have to generate a JIT every time. JVM already knows that these code patterns are hand-optimized. Just get the hand-optimized version. Vectorization and loop unrolling. So vectorization is basically using your processors. If your processors have SIMD instructions, which is single instruction, multiple data level capabilities, then you will use those instructions, and that way you can achieve data level parallelism. Loop unrolling is similar to what you know in static compilers as well. Runtime. Compressed oops, I already mentioned, compressed class pointers also help in throughput. Actually, with the introduction of compressed oops and class pointers, I've seen up to 35% improvement in many heaps. Actually, prior to JDK 7, we could only do up to like 32 gigs. So if your heap was 64 gigs, you would see up to like 35% benefit with compressed oops and compressed class pointers. Compressed class pointers are, I think, in JDK 8, introduced in JDK 8. So now if I want to talk about optimizations with respect to garbage collection, I could put all that, the list that I had mentioned separately together. So these are the optimizations, or the main optimizations, with respect to garbage collectors. You have faster allocation paths, faster reclamation, work done concurrently, multi-threaded work stealing, multi-generation, multi-phase marking, incremental compaction, compaction in general, and then allocation refinements and compressed headers. So now comes the fact, okay? Throughput and latency are the two main drivers towards refinement of GC algorithms. So what that means to me is that we're only interested in these two, at least in today's session. But in general, you will find more people, and actually the default up until Java 9, default collector is the throughput collector, which is also known as parallel GC or parallel old GC. And in Java 9, the default collector, garbage collector, is going to be garbage first garbage collector. So, so note that it would have compaction of some sort and all those other things. In fact, G1 GC also has concurrent work, and I'll talk more about that. So let's look at multi-generational heap. Another fact is almost all GCs in OpenJDK HotSpot, so basically except Shenandoah, are generational GCs, so they're optimized for throughput. So when I say multi-generational, I mean there is a young generation, like I said, and an old generation. The young generation is further divided into Eden and survivor spaces, okay? So again, let's put it into something that we all know, your conventional Java heap, right? We have the young generation and the old generation, and the young generation is further divided into Eden and survivor spaces, S0 and S1. People also know it as to and from space, okay? So most allocations will happen into Eden. After you age them, they will move into one of the survivor spaces, and then eventually, after they pass an age threshold, they'll be promoted into the tenured space. So GC, like I said, does allocation. I mean, not does allocation. The allocations are done by your allocating threads, but it handles optimizations. All the optimizations go under the GC heap management umbrella, and reclamation. So if I again put these optimizations from the throughput and the latency responsiveness side, we can say the faster allocation paths are, of course, allocation-related optimization. Multi-threaded work stealing is a garbage collection, which is reclamation part of the optimization. Faster reclamation as well. Multi-generational heap would be for allocation and promotions, because remember, multi-generation is where you make young objects die in the young generation, and then you promote them after they have crossed the age threshold. And it also belongs to reclamation because it helps with, especially young generation, is always stop the world, right? Whenever you have a young generation in OpenJDK HotSpot, all those garbage collectors perform stop the world, which is compaction. It does compacting, copy to survivor. More work done concurrently is the reclamation part, because we're doing marking and sweeping concurrently. And multi-phase marking, again, is reclamation. Incremental compaction also a part of the reclamation. So let's look at some allocation optimizations, basically these two, faster allocation paths and multi-generational heap. So remember I said most allocations happen into the Eden. So, and the way they happen is, like I said, thread local allocation buffers. They happen into, so each thread has its own allocation buffer. So if I had to draw a simplified version here, I can show you that these are areas inside the Eden space. Okay, so I have 5 threads. I have 5 TLabs. At the start, they are depending on the number of threads, but eventually it depends on the allocation patterns of these threads. So a particular thread could have a resized TLabs, which would be bigger than the other thread that has a smaller TLab, and it's based on the allocation pattern after every GC. Okay. So once the allocations, once the Eden gets full, you'll see that objects are moved to one of the survivor spaces. So now, reclamation. So basically, your heap is full. At least one generation of your heap is full. So you want to reclaim space back. Okay. And let's look at the optimizations for reclamation. We have, like I said, all these multi-threaded, multi-phase marking, multi-threaded work stealing, and stuff like that. So let's look at that now in terms of these generational collectors in OpenJDK HotSpot. So for all these generational collectors, you'll have similar GC algorithm for young collection, okay? The only thing changes, so basically what I'm saying is between garbage first garbage collector, the throughput collector, and the concurrent mark sweep, or mostly concurrent mark sweep collector, the major change is in the old generation collection, okay? So when we talk about the differences, and when I say that concurrent CMS is not compacting, I'm only talking about the old generation, because young generation is always compacted. When I talk about incremental compaction in G1, GC, I'm only talking about the old generation, okay? Something very interesting in mind is that you should remember that it's for old generations only. So let's look at parallel GC. So parallel GC is what I call the throughput maximizer. It has multi-generational heap. It has multi-threaded workers, which do work stealing and handle work queues. It's a compacting collector, which means the old generation is compacted in a monolithic fashion. It has faster reclamation via PLabs, and then, of course, it has TLabs. All of them have TLabs. So, and PLabs are promotion local area buffers. Just like your TLabs, you have promotion local area buffers for your old generation as well. So I call the CMS GC as a latency-sensitive GC. And that's because you have the multi-generational heap, and you have multi-threaded workers in some of the phases of multi-phased marking. And there's more work done concurrently. So remember when I said responsiveness? When you do more work concurrently, your application is more responsive because you're breaking down the phases, and which is what multi-phased marking is all about. You do something in parallel and something in parallel but in concurrent way, and your application is also working at the same time. So if you had to ask me, G1 GC is right somewhere in between. So you have all those things on the right, except that now we don't have a monolithic compaction of the old generation. We have incremental compacting collector, old generation collector, and then all the things from the on the left, which is latency sensitive. So it's kind of, so to speak, best of both the worlds. But of course, you know, depending on the application, one of the collectors will fit better than the other. But remember, in Java 9, G1 GC is the default collector. So how about compilation engine? So again, putting all those things together. And remember I mentioned that profile-guided optimization and adaptive optimizations are the two main things used in HotSpot, OpenJDK HotSpot. So let's look more on that. So it's very simple. The idea is very simple. HotSpot will identify performance critical methods. And the way it does, it has a compile threshold. Okay? So it'll try to identify the root of compilation and maybe try to JIT from there, from the root of compilation or just the method itself. There's two ways it can JIT. It can do the entire method, or it can do a loop. So it has this, backward counters where it sees these loopbacks, and then it could just do an on-stack replacement. So it doesn't do an entire method JITting. It does something called on-stack replacement, and so it can do either or. And there are three. Actually, before tiered compilation, you had two different levels of compilation. One was the startup optimized, also known as the client compiler, which is also known as C1, and which was the simplest. It was didn't have many of these optimizations that C2 would have. It had a very low compilation threshold. Basically, if your method has those many invocations, like 1,500 invocations, it will get compiled. Not to a higher, not to a advanced level of optimization, but it'll get compiled, JIT compiled. And then there's the other flavor, which is called the server compiler, also known as C2. And basically, the server compiler would start an interpreter just like your C1 would, but the compilation threshold, that is the method invocation count, is 10,000. So remember, compared to 1,500, it's 10,000. And now it has many performance optimizations that could be done. So, so you have a long-running application. It has these hot methods, and they cross the compilation threshold pretty quickly. And they will get JITted with higher performance optimizations. And then came tiered compilation. Tiered compilation is enabled by default in JDK 8. And it opens up a whole new level of possibility, because what happens is now you have 5 different levels of compilation. The first one is, of course, your interpreter code, and then the second level is called like simple compile. So basically, you compile. You have a very low threshold, try to compile, and there's no profiling information that's gathered. The third level is client compiler with some of those methods getting profiling information. The fourth level is client compiler with full profiling information. Now you have everything you need to know to be able to put in all the optimizations, the advanced optimizations that come with the server compiler, and that's the 5th level. The 5th level is the server compiler. So it's like tiered up until it reaches the max level of compilation. That's pretty much what I mentioned. So there's one effect on code cache with respect to that surfaced with respect to tiered compilation. And remember, I mentioned tiered code cache. It stores your compiled code for reuse, right? But with tiered compilation, what happened is, remember the first level, the C1 compilation, there are only 100 invocations. So remember, if your method gets called 100 times, it's going to be compiled. So remember, where's the code going to go? The compiled, the JIT code? It's going to go in the code cache. So now every method that's called has 100 invocations is going to go sit and get compiled and sit in your code cache, and your code cache is going to get bloated. And actually, we noticed that on JDK 8, we had to increase it to 5x to 240 MB versus prior to JDK 8 when it was only, the code cache was only 48 megabytes. If you need more, you can use that option called reserved code cache size. Okay. What about the advanced? This is the backbone of HotSpot JIT. It's the adaptive optimization. Okay. So the plot is very simple. You have startup which you do in interpreter, and then you have profiling information, and this is provided for these hot methods. Remember, you have these thresholds once these methods cross this threshold, you can start JITting them. So you want to get as much of profiling information as you can. And then you perform, like I said, the JIT optimizations. Sometimes you do deoptimizations, so that's why the error comes back, because you have different levels of JIT. And then the optimizations can take you back into interpreter sometimes. So that's the whole plot of how the HotSpot adaptive optimizer works. So let's look at deoptimization. Okay? So basically, these are your oopsies. So you have dependencies that may get invalidated. Like I also said, like because of tiered, you have different levels of compilation. So you may want to, deoptimize the code that you no longer need. You have uncommon paths in the compile code, and sometimes your profile information is wrong because you thought it was going to be a hot method. You went ahead and you compiled it, and it's no longer needed, right? So you just had misguided information. Intrinsics. Remember I said the intrinsics are slightly different than what you may be aware of. So you have the same sequence. You have the Java method, and you want to call JIT compilation on that, and then you want to execute the optimized code. But now you can call the hand-optimized assembly code directly. So you have these stubs, the hand-optimized code, so you don't need to go through JIT compilation or compilation every time. You just get these stubs for these special code patterns, and you can execute the optimized code, okay? And we have it for like our system array copy and all those things. So there's lots of optimizations done with respect to intrinsics. Intrinsics also don't need JNI calls, right? So if you had to do it in your program, you would use JNI call to have this hand-optimized code. But intrinsics don't need that. So it's really, really fast. The next one I want to talk about is escape analysis. So remember, all you have to find out is if the object escapes the method, right? So it applies to the entire IR graph. So how do you do that? You have to make sure it's not stored in a static field or a non-static field, but of an external object, right? Second, it's not returned by the method. If it's returned by the method, it's escaping, of course, right? And third, it's not passed as a parameter to another method where it can escape, right? So these are the three checks that you want to make sure and provide. And so basically, as long as the allocated object does not escape the compiled method, plus is not passed as a parameter, you can remove the allocation and keep the field values in registers. You don't need to do the allocation at all. That's a very good optimization. What if the allocated object it doesn't escape, but is passed as a parameter? You can still do some optimizations and compare instructions and stuff like that. So these are the two optimizations with respect to escape analysis that are present in the HotSpot virtual machine right now. What about the runtime? So putting everything together that we discussed earlier, let's look at compressed class pointers and compressed oops. So remember I mentioned about your Java object? So you have the header and the body, right? So a couple of points before we dive into these optimizations. Objects, Java objects, are 8-byte aligned, okay? This is the default. All objects are 8-byte aligned in Java, in HotSpot especially. Fields are aligned by the type. Fields can be moved to fill a gap, right? And are accessed using offset from the start of the object, okay? With these in mind, let's look at the Java object layout in memory. There's a tool called Java Object Layout, JOL, and it's to analyze Java object layout, of course. And I'm only going to use one of the options here called internals. So to be able to see object internals, field layout, and default contents, including the object header. Okay? So when you run the tool, you'll get notifications like this. So if you're using the 64-bit HotSpot virtual machine, by default, you will get, depending on your heap size, you'll get compressed oops with 3-bit shift and compressed class with 3-bit shift, okay? So the 3-bit shift, and that's the most important part, and that's what is compressed oops all about. So let's talk about that first. Remember I said all objects are 8-byte aligned? So if you left shift it by 3, we can have 2 raised to 35, which is 32 gigs of addressable space, right? So if I put this in the way the optimization works is basically this much. So wide OOP is nothing but your 32 gig of address space. This is for reading. When you're reading, it's called a wide OOP. And then the narrow OOP is your compressed reference, right? And it's used for storing. So when you're storing it, you want to have a compressed OOP, so you can store it compressed format. So you're using the optimization of 8-byte alignment to use compressed OOPs. And then there's the field offset, because that's how you access your fields, right? All right, so compressed OOPs has taken a lot of mature optimizations, and I'm summarizing them here. So if your heap size is less than 4 gigs, so you're on a 64-bit operating system, you're using a 64-bit JVM, but your heap size is less than 4 gigs. You don't need any encoding or decoding. Just use the narrow OOP. Your narrow OOP is a wide OOP. So basically, a compressed reference is the same as your addressable space. Oh, sorry, I didn't mention that. So if it's between 4 gigs and 28 gigs, then it's called zero-based. So now remember I mentioned when I showed you the formula, there was a base. You don't need that at all because you're between. You're less than 32. So you just need to shift it by 3. Okay? What about if you're greater than 28 but less than 32? I remember I said in reality there's a quirk. So at that time you need the narrow OOP base as well as the field offset. But when I say you need it, this is what the JVM does by default for you. So you don't have to do these calculations in mind. What I'm trying to show is how JVM is optimized for performance already. This is already, so you give it a 32 gig, less than 32 gig heap space, it'll perform that optimization, which is called the regular compressed OOPs. If you give it less than 4 gigs, it'll do no encoding, no decoding necessary. What is interesting in JDK 8, I think by default, the object alignment can change based on your heap size. So if your heap was less than 64 but greater than 32, your alignment could be changed to, instead of 8-byte, it would now be 16. So what that helps is now we can have 4 bits. So we change by 4 bits, and now you can have compressed references. Now remember, because you're changing the alignment, you're wasting heap space, right? So you have to do the trade-off and see if it's helpful. But that's something that JDK 8 allows you to do. Okay? Putting it all together again, which is the same stuff that I mentioned. So less than 4, you don't need an offset. You don't need to shift. Object alignment is 8 bytes. Greater than 4, less than 28, you don't need an offset. You do shift, and it's 8-byte. Less than 32, you need an offset, and you shift, and again 8-byte. And less than 64, you need 16-byte of alignment. Offset is required, and you shift by 4. Okay. This is, I think, my time. Is it? Oh, 10 minutes left. Yay, cool. Awesome. So now I'm going to go. This is my time, right? So, yes. Well, what is going to happen is you guys will get these slides. And what I did here, I just want to quickly go. So I expanded the header to try to show you how compressed OOPs and compressed class pointers actually work. And you have the mark word, you have the class, and then you have array length if it's an array object. And then I went and showed you some samples from using the JOL and showed how it, so basically, I'm just going to use this arrow quickly. So these are just examples. And I showed how compressed versus uncompressed looks. Sometimes the space is lost because of padding issues. But what is important is that there's 4-byte gain. So basically, that's because of your compressed class pointers. Okay? And then compressed oops, for that I used a class, and I showed how in uncompressed it's 8 bytes, and then in compressed it's all 4, and also the header is reduced to 12. So you gain 4 bytes because of compression, and then 4 bytes each for your class things, okay? So we covered both of those things. And then I had some talks about vectorization, octavectorization, but you'll get that. There's a paper that I've linked over here. HotSpot doesn't have all of that in place right now, but it does. It's trying. That's the optimization that they're going for auto-vectorization, and that is all that I had. Thank you.